In this here Chalk Talk, we're going to be talking about one of my all-time favorite topics, robotics. But specifically, we're going to explore a technology that plays a critical role in making robots smarter, safer, and more precise. Position sensors. From industrial automation and collaborative robots to autonomous mobile robots, knowing exactly where a robotic arm, joint, wheel, or actuator is located at any given moment is absolutely essential. Position sensors provide that real time feedback, helping robots move accurately, respond quickly, and operate reliably in dynamic environments. But not all position sensors are created equal. You want robust and reliable position sensors. And folks, that's exactly what we're talking about today. Hi, I'm Amelia Dalton, host of Chalk Talk. In this episode of Chalk Talk, Atanas Dikov from Melexis and I take a closer look at the key challenges in robotic motion control, what designers should consider when choosing the best sensing technology for their next robotic application, and the benefits that Melexis position sensors can bring to your next design. And before we get started, don't forget to click that link. There you can find even more information about this topic from Melexis. Hi, Atanas. Thank you so much for joining me.
Hello, Amelia. Amelia, thank you very much for having me here.
Absolutely. Okay, so we're talking about precision sensors for robotics today. Now, Melexis offers a variety of different solutions for these kinds of applications, right? How do these different inductive and magnetic solutions compare?
We're looking indeed at a portfolio that spans both magnetic and inductive technologies and position sensors. In fact, that would be the focus of the code today. Our portfolio is built on flexibility. So we aren't just giving a sensor, we are giving our customers and partners a solution that scales from the fast, high-speed motors driving primary actuators, let's say with a resolution in the range of 20 to 14 bits, to the very high 22-bit resolution required for low speed and joints with very high precisions and high loads. So to explain how the two technologies compare to each other, I will start with magnetic position sensors, which are the preferred choice for high-density integration. Because the sensing element and the magnet itself are physically small, these solutions excel in tightly constrained designs where every millimeter counts. On the other hand, we also provide an inductive technology, which offers a unique set of advantages, particularly regarding mechanical flexibility and environmental robustness. While in some designs, they may require more space for the coils, they offer a superior thin profile solution and in-nature stray field immunity. So this is how we can position the two technologies together into the robotic joint applications. And this is exactly the flexibility and freedom we provide to our customers so they can easily integrate and achieve their goals into the robotic joint challenges today.
So, can we dig into the details of the high-speed inductive encoder you mentioned?
Yes, so you can see that we have the MLX 90514, which provides up to 16-bit resolution. And the MLX 90520 is our powerhouse here, offering up to 22-bit resolution with an accuracy better than 0.1 degree. One of the biggest headache savers for engineers is the robustness. These sensors, by nature, are immune to magnetic stray fields, and they can handle air gaps up to 2 millimeters. They also do not require a reference encoder for the calibration, and they are very easy for integration. It's very thin and flexible assembly. We give here just an example that a total solution of an encoder for robotic joints using our inductive technology, it can be lower than 3 millimeter design. So this is combining the target, the transmitting and receiving coils, and the air gap in between. Indeed, a total solution. As a maybe interim conclusion here, they're indeed a perfect fit for very compact actuators, or even sometimes the so-called pancake actuators.
Okay, so talk to me a bit about the digital signal processing aspect of this solution.
This is indeed very important. This is one of the beauty of those sensors that we are offering. So there are two analog front ends process the two coil set signals. So now we need to take a look a little bit into the block diagram of this product to understand it better. So we have two analog front ends that process two coil signals with two tracking loops for the synchronized calculation of the position of the speed and the acceleration of the rotor, so that the position can go through an acceleration and compensation unit, which is also on board of the chip. And in such a way, we can output two fully synchronized angles with zero latency at the end for the vernier computation. So this vernier computation also happens on board. How do we get the 22-bit resolution? In this technology, in these products, we are using the vernier principle. And this is what you have seen on the previous slide. There was an image presenting the vernier principle with the primary secondary coils. By synchronously measuring a primary and secondary angle, two coil sets at the same time, we can determine the absolute position across 360. So this is in fact how it is. And the resolution of this product scales with the number of the periods in the design of the customers. For example, 64 periods setup gives you a full 22-bit resolution, and as well, if it's needed for very small designs, like a 20 millimeter, for example, of a diameter, we can pick 4 periods or 8 and achieve a resolution in the range of 18 to 90 bits, indeed on the high side of the performance.
So, can we also take a closer look at the magnetic high-speed encoder you mentioned?
The Melexis 90382, it's a magnetic encoder. Typically, these magnetic encoders, position sensors, excel in tightly constrained designs where every millimeter counts. The Melexis 9382 can track up to 200,000 RPMs. So you can see out of here that it's dedicated for very high speed applications, but it can fit also low speed applications. And in the heart of this chip is our patent 3-axis technology, allowing for on-axis, off-axis, and through shaft configuration. So from that perspective, the chip is really very flexible. This provides large flexibility, integration of the encoders, and this is a challenge that we are now solving for our partners and customers. Say it is also a safety-ready product, meeting ZIL2 requirements or even ZIL3 in a dual die package. It's a fully integrated solution, like the inductive encoders we have reviewed in the previous pages. Everything happens on board. Compensation for speed and sudden acceleration also happens on board. And this product provides a self-calibration end of line or during operation, so customers can decide when to switch on and off this self-calibration. 16-point linearization, angle calculation on board, and many, many other things. In this magnetic encoder, we adopted the fast tracking loop and zero latency architecture from the inductive products into the magnetic to ensure the high accuracy in a real-time application.
So, what about calibration? This solution includes self-calibration, right? So, can you walk me through how this works?
Yes, I'm very excited as well from this feature. It's a self-calibrating or self-adapting to the surrounding environment, let's say. So the product is unique because it calibrates itself during operation or end of line, as I already mentioned. It automatically detects and corrects gain mismatch and orthogonality errors in the IQ signals. Customers and our partners can program the settling speed. For example, the fast settings we offer for the end-of-line calibration, and the slow settings is usually more suitable during operation where the product is in the field. which can significantly improve the performance of the overall final product, being a complete motor, actuator, and so on.
Okay, so based on what we've talked about so far, can you give me an example of a real world challenge that you helped solve here?
Yeah, so everybody is talking resolution. There is definitely a resolution hype, and this is great. But in real-time robotics, our data is dangerous because of propagation delays and heavy software filtering. The data often reaches the microcontroller too late, creating a phase shift in the control loop of our partners and customers. And this indeed could be dangerous, especially in future times and even sometimes in these days where already these robotic products are working alongside people. And how do we solve this real-time challenge? Is first of all with our tracking loop architecture. As I already mentioned, our encoders use an internal hardware-based tracking loop that provides zero latency. The position read is the real-time absolute position at the end. So this is what we deliver. The next feature and benefit for our customers in the on-chip dynamic compensation. As I explained, we provide speed and acceleration data directly from the chips. Doing this off-chip results in fewer samples, higher noise, and poor reaction to sudden motion changes, which it's very crucial for the future of the robotic application. So this should never happen. And the last one that I decided to highlight here is the SPI Super Frame mode. This is a synchronized sampling, so multiple ICs capture the position at the exact same time and send it in a single synchronized data frame. So you can imagine a pure example, it will be those encoders from Melexis integrated in different robotic joints of a humanoid robot. So they will be fully synchronized and the data will be provided at once from all the different locations of the robot. As a result, we offload the microcontroller, we are reducing the code complexity, and we are simplifying the hardware, ensuring the robot always knows its exact coordinate.
So, can we also talk about the Arcminaxis magnetic encoders as well? What kind of features are we talking about for this solution?
There is a name already on the table. So this is a new technology range within Melexis, like our 3-axis, but now it's Arcminaxis. What is the difference is that the Arcminaxis combines multi-axis sensor and a dual track magnet with a primary track and a secondary track. So already from the visualization, you can understand that we're talking about, again, for vernier type of application, vernier type of a concept, like the high resolution inductive sensor from Melexis, but this time is the magnetic one. Again, the same principle. The primary provides the angle and the secondary track of the magnet, the internal one, is used for the sector discrimination. And with the Melexis 90384, the angle computation this time happens with a special firmware that we provide from Melexis for any ARM microcontroller. The chip can provide up to 18-bit resolution with large tolerances in place, like plus minus 0.5 millimeter in any direction. As well provides a large air gap range up to 1.5 millimeter. Of course, it can also go low, so the chip could be close to the target, but also it can go up to 1.5 millimeter. As well, it's a pitch independent. This is indeed something unique of our solutions, and this is making the mechanical integration a piece of cake. Let me state it like that. So indeed, an easy integration for our customers and partners. And this is one more challenge that we solve with our magnetic and inductive encoders.
This solution comes in a kit, right? What's all included in the kit?
It is a kit, and this is what is different from the others we have presented so far. So you can see on the screen, it's a TSOP16 package with magnet. It's a customized magnet. It's a ferrite, and there are already 4 options on the shelf of different type of size of magnets. and as well thickness. So these magnets also could be thick, and it could be also in a very different size. In particular, our chip can work with any size of a magnet. And on top, we also provide the software for any ARM microcontroller. So it's a library and a software, and this is one kit offer for our customers.
What kind of supporting tools and assets do you guys offer here?
I have decided to share a few examples of the development kits and evaluation, let's say, equipment that we have already managed to build and to provide here and there. We start on the top is the inductive one, where you see on the left side on the screen, those are different targets with different periodicity as well to provide a different resolution. And you can already see that it can go very small in a size. Here we have an example with the 20 millimeter, the smallest one, and then larger with the 64 periodicity to provide the 22-bit resolution. It's a SPI communication, a standard one, nothing complex. On top of all of this, we as well providing an inductive simulator. We as well can support our customers of making the design of the coils, but with this inductive simulator is already a perfect start, and it makes the customer evaluation much easier. On the bottom side of the page are the two magnetic solutions, the MLX 90382, the development kit. So we can see that we provide an evaluation board with the so-called Melexis I/O. So this is like an SPI master to connect the chip to the computer. There is as well a graphic user interface that can be downloaded from the melexis.com site. On the right side is again a full kit. So this is like a full encoder solution with the MLX 90384 Arcminaxis. There you can get out of this the chip soldered on the PCB as a reference design, SPI master, and then the dual track magnet as one kit for evaluation. And this product as well comes with the GUI on at the melexis.com that can be downloaded and evaluated. As we already mentioned, the inductive simulator, we also provide a magnetic simulator and can be accessed on our website.
Fantastic. Well, I think that's all I have time for today. Thank you so much for joining me.
Thank you very much as well for your time and your support. Thank you.
And before we go, you didn't forget to click that link, did you? There you can find even more information about this topic from Melexis. For Chalk Talks, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, head on over to the Chalk Talk section of EE Journal. You can't miss it, it's right across the top. Or head on over to YouTube, youtube.com/EE Journal.